So this is a project from 2013 PTAC funding, but this really comes back from my personal perspective from something that was bugging me probably a full 15 years ago when I was working as a hydrogeologist back in the early COMEX days. And it occurred to me that we were spending quite a lot of time we do a lot of routine groundwater monitoring. We monitor, typically upstream facilities. We monitor hydrocarbons. We monitor salts, and quite often we feel obliged to monitor metals. And what was happening so often is we'd monitor metals, and then we'd get all of these exceedances of whatever the guidelines at the time were, and then let's move that in a little bit, and then once we'd done that, we would have all of these exceedances, and then we would spend a chunk of time justifying why these exceedances weren't really related to any of the site-related impacts, go around that circle, and then possibly identify a couple of metals issues that were relevant, and on we would go. And then the next project would come around, and we would spot the same metals sort of spuriously coming up, exceeding guidelines. We say their background. And it's always been in the back of my mind to just take a bit of a closer look, have a think about which of these metals we are actually choosing to analyze at these upstream sites, and try and have a bit of a think about which ones are actually relevant to what we're doing, and which ones are just going to be spurious time and time again, and see if we could maybe exclude those from certain categories on the site. So just to provide a sort of a disclaimer right up front. This was a very small piece of PTAC funding. We just got a little bit of money just to take a preliminary look at this to see if that was of interest, and see if we could get some data to look into that. So again, last year's PTAC funding. So overall, the objectives of this project were to consider routine groundwater monitoring at upstream sites, and give some thought to whether we actually need to monitor all of those tier 1 groundwater metals. And if and whether we do or not, to see if we can come up with a rationale for which ones it actually makes sense to monitor at upstream sites, and which ones maybe less so. So just to be clear about the scope of what I had in mind here, I'm thinking really that something that would be applied to what I'm calling sort of standard upstream oil and gas well sites. The sort of sites we've got dozens and hundreds and hundreds of around the province. We're not thinking any of the large facilities like gas plants, where there might be a range of different oddball chemicals that we might not be considering. Definitely not considering any thermal facilities, so facilities that would be putting heat into the ground that can change the geochemistry of the soil. And obviously, if there was a facility that had a particular reason for being concerned about a particular metal, that's another thing that we wouldn't be sort of considering in this scope. So just basically sort of your average standard oil field upstream oil and gas well site. So here are the numbers. These are the 17 metals in the tier 1 guidelines for which we have tier 1 groundwater guidelines. You can see there, some of them are quite large, in the milligrams per liter. Most of them are sort of smallish in the micrograms per liter, and a couple of them are tiny in the nanograms per liter range. But what's again, in the interest of full disclosure, should mention that just for the sake of having a number to put in this table, I've picked the agricultural land use if it matters. And for the metals that vary with where the guidelines vary with hardness, I've picked an arbitrary hardness of 100 milligrams per liter. So those are our tier 1 groundwater guidelines, and it's probably not a surprise when some of the numbers are as small as they are that we would sometimes get background groundwater concentrations exceeding those numbers. But the thing that's probably worth pointing out here, the fact that these particular 17 metals appear in the tier 1 guidelines, it's not that anyone, nobody sat down and thought, okay, which of these metals are likely to come up in the sort of sites we see in Alberta, and we'll include those. Really, pragmatically, it was much more a case of which metals do we have data from which we can develop a tier 1 guideline, and we'll just have numbers for those. So we sat down and tried to think about what are the considerations that we might pay attention to to determine which of these metals we might reasonably expect at upstream oil and gas sites. And the first of those issues, it's not really a consideration directly, but we wanted to have a look at what the range of background concentrations of these things in shallow groundwater, just to put our work into context. A minor point is that some metals, as we know, can be liberated during anaerobic biodegradation of organic compounds, so that was a factor to be considered. One of the main ones we wanted to look at is which of these metals. Well, first we were thinking which of these metals can be in drilling mud components, and then we refined that thinking a little bit, because a lot of those drilling mud components are natural products. If you've got a sufficiently good detection limit, probably all of these metals are present in some of those in some of those components. And so we were really asking ourselves the question: which of these metals can be present in oilfield drilling mud components at high enough concentrations to be an issue, to be significant for us? And then the fourth consideration was, well, do any of these metals, can they actually be present in oil field formation waters at high enough concentrations to be a concern, so that when we have a release of produced water, the concentrations of metals in that produced water are of concern? So the rest of the presentation is going to sort of step through those four issues in turn. The background issue, we approached that by a little data mining exercise conducted by Daniel Pollard, who's in the room today, very kindly. This is not the last word on metals concentrations in background, but it is a good context piece, I believe. What we did was we took a large database of metals concentration in shallow groundwater in Alberta. And then we used a fairly broad brush, high-level approach to exclude, hopefully, the vast majority of contaminated samples. And so the criteria we used was that anything that had detectable concentrations of hydrocarbons was out. Anything that had detectable concentrations of any other organic chemicals, processed chemicals, glycols, amines, anything like that was out. Anything with chlorides greater than 100 milligrams per litre, that got excluded. Anything with pH outside the normal range was excluded. So we used those sort of criteria to bump out the obviously contaminated samples. I don't say there's not a few contaminated samples left here, but what remains, I think, the vast majority are indicative of a background concentration. So that was the first step. And then the second step was for each one of those metals to divide the concentration by its respective Tier 1 guideline. And obviously, we didn't do anything as sophisticated as calculating the appropriate hardness specific guideline. So this is again fairly generic data just to get a first look at this. But by calculating the ratio of those background concentrations to the Tier 1 guideline, we were able to compare the distribution of background concentrations on an equal basis from metal to metal. So I think it is an interesting and useful presentation. So we've got all of the Tier 1 metals here. And for instance, it lets us see some things immediately. So a few metals, and this one here, I believe, would be, I think that's chromium. I'm looking kind of sideways at that. So a few metals, all of the background concentrations that we had were, say, an order of magnitude below background. So we're not really expecting ever to see a spurious Tier 1 guideline exceedance of that metal, unless that guideline exceedance is related to anthropogenic input. And maybe same thing here, and this one's silver, and as we know, we very rarely see silver being an environmental contaminant of concern. And then a very small number of contaminants where the background range is pretty much always actually above the Tier 1 guideline. That one's uranium. But for the vast majority of these metals, the distribution of what we're seeing as a range of background concentrations cuts that Tier 1 line. And so that immediately gives us, significant concern when we're trying to use those tier 1 metal guidelines to draw any useful conclusions from groundwater monitoring. What we're seeing is that for most of those metals, most of the time, we're going to be expecting to see background concentrations exceeding tier 1. So really, I wanted to start with that, just to put our monitoring concentrations in context and just show what a significant concern the fact of the relative juxtaposition of the tier 1 levels and our typical range of background is. So that's background concentrations for context. Second of those 4 considerations was anaerobic biodegradation. This one's easy in the sense that I think most of us are aware that both iron and manganese can get released during, if a site gets appropriately anaerobic, iron from unavailable, insoluble iron 3 ferric iron can get reduced to ferrous iron, which is soluble, manganese going from oxidation state of 4 to 2. So essentially anaerobic biodegradation can significantly increase the concentrations, the soluble concentration in groundwater of both those 2 metals. So it makes sense that those should always be included in groundwater monitoring upstream sites. The more complicated piece was the drilling mud. We were very fortunate in having a lot of cooperation from a company called Marquis Alliance, who sell drilling mud components, basically. They, after a significant amount of discussion and let's just say persuasion, agreed to share with us metals analysis for their entire suite of drilling muds. Now, I'm certainly not at liberty to share the actual analysis of the individual proprietary components. But as a whole, we were able to look at metals analysis for a suite of 314 different components that get used in oil field muds. Now, another sales company, another manufacturer, there's probably some other components, there's some other possible compounds that we don't have there. But we've got a pretty conclusive, a pretty comprehensive set of potential mud components. So we had this vast mass of data, each one, some of them have high metals, some of them have low metals. The approach that we took here was to consider our 17 metals one by one. And for each metal, we would look down the list of these different components and pick out the component that had the highest concentration of that metal and take a look at that one. And just to be clear, these analyses, most of these mud components, they're solids, they're powders. And so the analysis that we had were in terms of solid analysis in milligrams per kilogram. And we chose to compare that maximum metal concentration in whichever component had the highest concentration of that metal to its tier 1 soil remediation guideline. Because we felt that if the highest, if the worst possible mud component met the tier 1 soil guideline, it really wasn't going to be a problem. And then we calculated a kind of a ratio, essentially. So we calculated the ratio of that maximum metal concentration in any drilling mud component to the tier 1 soil remediation guideline. And then we grouped the metals into 3 very broad brush groups. First one was easy, so we said if the worst possible case, if that ratio is less than 1, then any of these components, even if you just dump that pure component in the ground, they meet tier 1 and it's a non-issue. That was an easy one. And then pretty much arbitrarily we said that if the ratio of that maximum concentration to the tier 1 guideline is more than 10, then there's at least one component here with a significant amount of this metal in. It may or may not turn out to be an actual issue, but it's enough that we're just going to include that. We should be including that. And then we had this group where that ratio was between 1 and 10, and we said, well, we should look at that more closely to see whether this is a component which is used in vast bulk in drilling mud, or if it's something that's used in relatively trace quantities. So these are the ratios that we came up with, and just ranked in order from highest to lowest ratio. And so as you can see, we've got 7 metals there which meet that what I'm categorizing in red, that's where that ratio is 10 or greater, all the way up to zinc at 2800. In orange are 4 metals that fall in that 1 to 10 ratio in the range 1 to 10, and then the 3 metals in green are ones where the ratio is less than 1. So, essentially from this point, any of the metals in red, we felt we should be just including those anyway. There's significant amounts of that metal in one or more drilling mud components. So it's there's value and validity in continuing to analyze those. And similarly, those 3 metals in green, if those are the very highest concentrations in the worst component, then really there's very little concern from drilling mud. For the orange ones, what we wanted to do was say, well, what are these components that have the higher concentrations of those metals in them? And so we sort of dug into this a little bit, and for the component with the highest concentration of each of these metals, we said, well, what is it? What does that component do? And there's various things in there. The red ones really don't concern us that much because we know we're going to be analyzing for those anyway. Zinc's an interesting one though, because actually zinc carbonate, I didn't know this, zinc carbonate is quite widely used as a sulfide scavenger in muds. If you've got a little bit of H2S, having zinc carbonate in your mud will manage that. Others are deflux, weighting, or obviously barite, as we know, is a weighting agent. The interesting ones though with the cadmium, arsenic, antimony and lead. And a couple of those were used as LCM, lost circulation mud, or lost circulation additive components. And cadmium was showing up in some of the deflocculants. But basically we looked in some detail at exactly what these components were and how they were used. And all of the orange ones are used in, I wouldn't say trace quantities, but certainly well less than 10%. And so we concluded that for the metals in that orange group, really even in the worst case of any mud you might reasonably mix, even the mud would meet Alberta Tier 1 soil guidelines itself for those metal contents. So we felt that we could probably safely exclude those orange ones from the mud considerations. So in summary of that, the green metals, silver, uranium, mercury, really don't seem to be present in significant contents in drilling muds. Cadmium, arsenic, antimony and lead, we felt were not a concern. While they could be present at above Tier 1 guidelines in some mud components, that product would always be used in significantly less than 10% of the mass of a mud, so we felt it was reasonable to exclude those. And then the other metals, so zinc, boron, nickel, copper, barium, chromium and selenium, they can all be potentially present in mud. And I don't think any of those metals would be a surprise to anyone. Those are the sorts of things that we typically do come across. And those can potentially be present at significant concentrations. So we started with 4 considerations. The last one was formation waters, produced water / formation waters. And the approach that I'd intended to use going into this project was to talk to my various friends in industry, and I was pretty sure that it would be possible to track down formation water analysis that would include metals analysis. And it may still be the case that those data exist, but I've totally struck out with persuading anyone to share those data with me, or even admit that they exist, or even find the right people who have access to them. If anybody is aware of those data existing and being available, or would know who to talk to, I'd be very interested to chat with them. But after banging my head against that brick wall for probably 9 months off and on, I just sort of backed up and said, well, let's find another way to approach this. And say, well, if these metals are in produced water at concentrations high enough to be a problem, then surely we would see them in shallow groundwater. And not only that, we know that produced water, where it's concerned, almost always, not invariably, but very often contains high concentrations of chloride. And chloride is basically our oilfield tracer for produced water. And so if these metals are a concern in produced water, then if we go back to our data mining approach, we should see some correlation between metal concentration and chloride concentration. And so where we see the shallow groundwater with higher chloride, those ought to be also the samples where we see the higher metals, if indeed those metals are coming from the produced water. Or if we see no correlation, then we would draw the conclusion that in fact what we're seeing is just a natural background variation which is unrelated to the distribution of chloride. So that was the secondary approach taken, and it may, I still want to give it some more thought, but I think that may actually be a more practically useful approach than working with the original formation data. So here was an example. This is uranium, just to pick one at random. So what we've got here, just talk through this slide a little bit, we've got chloride concentrations along the x-axis, and as we know, we arbitrarily use 100 milligrams per litre as being the sort of perhaps uncontaminated or contaminated with produced water threshold. But as we go to the right on this graph, we're expecting that anything over 100, and as we get into 200, 300, 400 milligrams per litre, those are basically the samples where we're assuming that those are impacted with produced water. And what we see is some uranium concentrations going up relatively high, 300 micrograms per litre. But the highest uranium is at effectively less than 10 chloride, and there's really no significant correlation between the two. And so in this case, I would interpret that, again, it's not the ultimate data set. I'm sure we could go and collect even more data and be more certain. But I would look at that and say with a reasonable high degree of certainty that uranium is related to random variations in the background and is not coming from, it's not correlating with the chloride, and hence is not coming from the produced water. So we went through that same approach for each one of the metals in turn, and what we really found is that we weren't seeing significant correlations between metals and chloride for pretty much all of the metals that we were looking at. I don't have time or space, or I'm sure you would get bored rapidly if I start going through all of those correlations. But just to summarize them, we really found that for 16 out of those 17 metals, there was just no plausible correlation between, in the data set that we had, between chloride concentration and metal concentration. And so we came to the conclusion that in fact metals coming out of produced water doesn't seem to be necessarily one of the driving factors for what we're seeing in shallow groundwater. The exception was barium. We seem to have some correlation there. Again, I'd like to see more data. It doesn't actually seem that likely to me that barium would be related to produced water, but again, it's possible. But the data weren't strong enough to say that, to really exclude it. But we know that barium's in drilling mud anyway, so that's, barium's going to be on the list. So that's where we got to with the produced water piece of this. And again, this is fairly preliminary. We didn't have the budget to go and do anything too extensive with this one, but essentially what we concluded was that there are, is that 9? Yeah, there were 9 metals that we would expect very reasonably to turn up at upstream oil and gas sites, and 7 of those, so that's the barium, boron, chromium, copper, nickel, selenium, and zinc, where we would expect to be in drilling mud at some, could be in drilling mud anyway, at a concentration that might give us concern, and then iron and manganese, of course, from biodegradation. And then we found that another 8 metals were things where really we couldn't find any rationale to say that these would be associated with upstream well sites from either drilling or production activities. And so these are the things that when we see exceedances of tier 1, we're really expecting those probably to be related to background, and suggest that we should give consideration to whether we actually need to be even monitoring those components in shallow groundwater at regular oil and gas sites.